In Chapter 8, we take a look at weathering and soil and mass movement. So what we're really going to take a look at in Chapter 8 is more of the sculpting of the Earth's surface. We've taken a look at volcanoes and earthquakes. We looked at crustal deformation and mountain building. So now we're going to continue on in looking at shaping the Earth's surface. So just to give you some definitions of this terminology, weathering is going to occur at or near the surface. And weathering is going to be done by some type of external factor, external force. Mass wasting is when we get a huge amount of rock material of some sort that goes downslope. This is what we're going to typically see in landslides, for example. And then erosion is when we get essentially weathering, we get transportation of materials, but we're going to have some type of mobile agent like water, wind, or ice in the case of glaciers, for example. Types of weathering: mechanical and chemical. Mechanical is a physical breaking of rocks, and then chemical weathering is done by some type of chemical. Usually this is going to be done in the form of rain or something like that, and we'll get to that, more specifics about that in just a little bit. There are different types of mechanical weathering. We have frost wedging, which is done by freezing water, and we see this in colder climates where there's a lot of snow and ice that are on the ground. We know that as water freezes, it expands. So when water seeps into cracks in rocks, as that water freezes, it expands and essentially breaks apart or creates wedges, cracks in the rock. So that's one type of mechanical weathering that we can have. Another type of mechanical weathering that we see is done by what is called sheeting. And sheeting is when we get this exfoliation, so to speak, of rocks that result from a reduction in confining pressure. We can also have salt crystal growth. This is something that we see along rocky shorelines or along the oceans, arid regions. When we have salty groundwater or sea spray that's coming off of the ocean, it can get into crevices and spaces within the rock. The water evaporates, but the salt crystals are left behind, and they continue to grow larger and larger, and that weakens the rocks by pushing them apart. This is seen, too, when we have areas that use salt on roadways. So in colder climates, not only do they have to worry about frost wedging, they also have to worry about what happens when they use salt on their roads to melt the ice. Then the salt is left behind and can create issues that are just as bad as the frost wedging. Then we also have biological activity, such as tree roots. Tree roots can grow into fractures in the rocks, and as they grow, they can wedge or split the rock apart. Organisms can also play a role in chemical weathering. So there are some smart figures that go along with these different types of mechanical weathering. I would encourage you to watch these because they're going to give you a lot more information. So here's one on frost wedging, and you can see how we have these giant fractures in these rocks, and this is due to the continuous, freeze and thaw that we see in some northern climates. We also have sheeting, and so this is an example of sheeting. This is at Half Dome within Yosemite National Park. And sheeting kind of leads to what they refer to as these onion-like layers. What happens is you get these plutons. And we talked a little bit about these when we were talking about volcanic activity. But this is a large mass of igneous rock. And it's formed underground, but as erosion takes off all of this ground on top, now there's no more pressure. And this leads to expansion. And as this expands and is uplifted, we get joints, and then we get these sheets. And if they become loose enough, they fall. So chemical weathering is looking at the breaking of smaller rocks breaking of rocks into smaller pieces by some type of chemical. So we're going to affect the internal structure of the minerals. And this is due to the removal or addition of chemical elements. During this type of transformation, the rock is going to decompose into substances that are stable within whatever environment they're in. The most important agent we see is water. We know that water is a great solvent. A lot of dissolved substances can be found in water. Pure water is non-reactive, but if we put just a small amount of dissolved material, then we can activate this power of water as a chemical weathering agent. Oxygen dissolved in water can oxidize materials. For example, rusting is an example of oxidation. Carbon dioxide dissolves in water to produce carbonic acid, and rain will pick up some carbon dioxide as it falls to the atmosphere, and as it percolates into the soil, it picks up more from decaying organic matter, and any type of acid can cause weathering of really any type of material. Carbonic acid can produce products that are water soluble. Calcite, which we saw earlier in the semester, would fizz when the hydrochloric acid was applied to it. Well, if we have large amounts of calcite, for example, in marble or limestone, and is exposed to carbonic acid, then it can essentially dissolve the limestone or the marble. Spheroidal weathering generates round rocks, and so if we look at outcrops, and there's a figure in your book on page 241, and this is a smart figure. I thought I had it in here. Sorry. Spheroidal weathering is because we have chemical weathering that's working inward from those exposed surfaces. Weathering is going to attack edges of rocks from 2 sides, corners from 3 sides. So they're going to wear down faster than a flat surface. So this leads to the rounded edges that we see at the bottom of page 241 in your book. Now, differential weathering is when we get different, rocks of different compositions that are going to be susceptible to differential weathering. So some parts are going to weather differently than the others. rock characteristics, such as what type of minerals are in the rocks, what their solubility is, what their physical features are, what is the appearance in terms of the shape or the cleavage of the rock. And then taking a look at climate. Climate is very important, especially if we look at temperature and precipitation. These two are critical to rock weathering. And so this is going to play a role in the type of weathering that we get. So this is Smart Figure 8.9. There is a video that accompanies this. This is found in the Badlands, the misty Badlands of New Mexico. And so we get this incredible landscape that is formed by all of these different processes. We have chemical weathering at play. We probably have some frost wedging that's going to be at play. This is a dry region, so we could even have some formation of salt crystals. And all of that is going to lead to differential weathering. So we get this really different looking landscape as we look at different areas around here. The next section of Chapter 8 gets into soil. And soil is made by these different weathering processes. This is also a boundary where parts of the system interact. We talk about where, the atmosphere, the biosphere, the geosphere all come together. So when we look at soil, it's a combination of several different things. Mineral matter, so things, pieces of rocks that are broken up by weathering, also composed of water and air. Regolith is the layer of rock and mineral fragments that we see that is going to support the growth of plants. So this is kind of that top layer that we see. And if we look at texture and structure, so texture looks at the proportions of the different particle sizes. So we can go from sand, which are larger particles, to silt, which are a little bit smaller, and then to clay. Loam is a mixture of all three. And what we're going to do in the lab is work with some soil and use some different tests to determine our soil texture. And then we'll classify that based on a particular soil chart and determine what type of soil we have. Is it sandy? Is it silty? Is it primarily composed of clay? Or is it a good mixture of the three to create loam? So we'll do that in the lab. We'll use this diagram to determine what type of soil we have. Now, the structure of soil, if we look at this is when we have soil particles that are clumping together. And there are 4 basic soil structures you see there. We can have platy, prismatic, blocky, or spheroidal. The soil particles are, not independent from one another. They're forming clumps, and soil structure is important because this influences the cultivation of the soil. So both texture and structure are important. So what are the controls of soil formation? So what determines what types of soil we have? Well, first of all, we look at our parent material. What's it made of? Is it residual soil from the bedrock that's being weathered, or is it soil that's been transported from other places? Time. We know that time is important in all of our geological processes. So the amount of time it takes to evolve varies for the different types of soil. Of course, climate, temperature, and moisture play a huge role in how soil is formed. Plants and animals. Plants and animals are going to furnish organic matter to soil. So the more plants and animals and the different variety of plants and animals that we have can determine soil. And then our topography. We have to look at the slope and the steepness of the topography.